So this is our last of 3 of the review recordings that I'm having you work through, and this one is again taken from material from chapter 13, and this one we are going to spend some time thinking about this single molecule adenosine triphosphate, or what is commonly referred to as ATP, and the reason being that, of course, this plays a real central role in the energy metabolism. We've already talked about it in class, we've already talked about it in the other review recordings, and we're going to talk about it really for the rest of the semester. So I think it's important to at least look at this molecule, and to think about what exactly it is, and that's what we'll do here first, and think about what kind of reactions it undergoes, and then secondly we'll think about it from an energetic standpoint. Now ATP is one of 5 different nucleotide triphosphates, so there are 5 NTPs. I would hope that you have talked about nucleotide triphosphates and what exactly nucleotides are. So a nucleotide is any molecule that has a phosphate moiety that's connected to a ribose sugar, and then that ribose sugar is connected to a base. And when you look at ATP, that's exactly what we see here. So this is the phosphate moiety, and it's really the business end of ATP in terms of energy metabolism, but that is connected then to this ribose ring. Obviously this is not shown in its full structure, just this box ribose ring. Oops. And then finally you've got this base. Now the base is what differentiates the 5 different nucleotides from each other. So we have ATP, which has this adenine base, but then there's GTP, which has a different base, guanosine base. We'd have UTP with a uracil base, CTP with a cytosine base, and then thiamine base, which will give you TTP. Right? Now, from a genetic standpoint, the function of these are very different. They're used to, of course, make DNA, to make RNA, and used in lots of different genetic aspects of the cell. This is what makes up as the building blocks of our genetic material. From an energy standpoint, there's not much different about these. These are all essentially equivalent molecules from the standpoint of the fact that the phosphate moiety is the same in all of them. Right? Now in energy metabolism you will see these 2 used fairly commonly, ATP being obviously the most common that's used in energy metabolism. CTP and TTP are rarely used in energy metabolism. Okay? And when we see GTP and UTP either made or generated from a catabolic pathway or used in an anabolic pathway, we talk about them as being ATP equivalents simply because from an energetic standpoint they are equivalent. Right? In fact, you can do this. Every cell comes equipped with enzymes to do this reaction. Let me get a different colored pen, where you have ADP plus GTP, or one of the other nucleotide triphosphates. I guess we could just say NTP. I can make ATP and NDP. Okay, so that's a very common reaction. There's enzymes that are found in all cells that can do this. So the other NTPs that we're looking at here are essentially energetically equivalent. Right? Now, let's go ahead and focus on this phosphate moiety, and let's say a couple of things about the phosphate moiety. First of all, you've got these different phosphate groups. The most outside one, or the furthest one out, is called the gamma phosphate, and then obviously the beta phosphate comes next, and then the alpha phosphate comes last. Now by phosphate we simply mean a phosphate atom that has covalent bonds to 4 different oxygens, 5 covalent bonds. Phosphate atoms have the capacity to form 5 covalent bonds, and that's what we mean by a phosphate group. And you'll hear that language used in biochemistry. It's not a phosphate atom, but it's a phosphate group that has this phosphate surrounded by 4 oxygens with 5 bonds to them. Now, one of the things that I want to mention in regards to these phosphate groups is that that phosphate is extremely electrophilic. It's a great electrophile because the electron drawing power of the oxygens that surround it make it a fairly electron deficient atom. That then makes it susceptible to nucleophilic attack by one of many nucleophiles, oxygen being the most common that's used, although nitrogen is another one that's used as well. We're showing it here with oxygen. Now you'll hear terminology in terms of the bond. You'll hear that of a phosphate anhydride bond, and by that we simply mean this bond here. Phosphate anhydride bond, there's another one here, there's another one here. Okay, so those are phosphate anhydride bonds, and oftentimes you'll hear them referred to as high energy bonds. Okay, now those electrophile phosphates can undergo this nucleophilic attack, as I just mentioned, and the products are slightly different when that happens. For instance, let's go back to purple here. If a nucleophile attacks the gamma phosphate, the result will be essentially this inorganic phosphate, PI, and ADP, adenosine diphosphate. So we've had one of the phosphates moved from the triphosphate moiety. This could be, by the way, and this I think it is important to mention, this here nucleophile, I'm showing it just as, and this is showing it just as really an oxygen, okay, but that could be any number of groups, and we'd say that that molecule, whatever this R is, has been phosphorylated. For instance, that could be an oxygen coming off of a protein, and that phosphate group then has been transferred to a protein, and that oxygen could be, let's say, coming from a glutamate or an aspartate. Okay, so it really depends, or a serine, or a threonine. So it really depends on the scenario, what exactly R is. Now the next potential point of nucleophilic attack and substitution would be, of course, the beta phosphate, and that's going to lead to AMP and pyrophosphate, or just PPI. Again, depends on what R exactly is. Delta G for this reaction, that standard condition, is equal to negative 45 kilojoules per mole, or about negative 45 kilojoules per mole. For this reaction over here, the delta G is equal to negative 30.5 kilojoules per mole. Okay, so there's an energetic difference. The most common of reactions is this one in purple. The one in green is somewhat common. We'll see it in several scenarios in this class. And then the final one, which I haven't really even talked about, where the alpha phosphate is going to be attacked by a nucleophile here, right, which also results in PPI, pyrophosphate. But what happens here is the adenylate group is transferred, and we would say that this molecule, whatever R is, has been adenylated, not phosphorylated. Okay, this is by far the least common, and there will only be, I think, 1 or 2 scenarios where we talk about it, if that. I'm trying to think if that's true. I have to go back through my notes, but we won't see this very common. We'll see the other 2 quite commonly. Okay. Now, when you start to think about this, I think it's important to mention this, right? There's lots of reasons why the delta G of this reaction is so exergonic, and your book discusses those. I don't feel that it's very important to mention those. You can certainly read those on your own. There are good reasons for that, and your book, I think, does a fairly decent job of discussing those, why they're so exergonic under standard conditions. I do want to mention this, and I think that this is important because it's in line kind of with why they're so exergonic, and while it's also very important in terms of why this molecule is used so often. This inorganic phosphate, so let me draw it here. I'll draw it in purple, or green, I guess. But inorganic phosphate here, okay, It's often drawn like this, where it's got this double bond, right, and then it's got these negative charges on these atoms, those oxygen atoms. In reality, though, that double bond here, right, exists in a resonance stabilized form, so that the more accurate depiction of this would be like this. And your book discusses this as well. And that resonance stabilization makes that phosphate group a really good leaving group. And we talked about that in our last review, that one of the strategies of metabolism is to undergo nucleophilic substitution reactions in which a good leaving group is attached to a molecule. This represents a really good leaving group because it can undergo that resonance stabilization. It's actually a very stable entity. So that's an excellent leaving group. Okay, so that's the molecule ATP, from what exactly it is and the reactions that it can undergo. Let's go ahead and look at this from an energetic standpoint. And over here, table 13.6, we see this table where we have standard free energies. Okay, and they're really, the table is standard free energies of hydrolysis of some phosphorylated compounds. And let me go ahead and highlight for us here the most common means of using ATP, and that is to make ADP an inorganic phosphate. And what you'll see here is that this really sits in kind of the center of this table. It certainly doesn't have the most exergonic standard free energy change of hydrolysis. There are molecules above that. There are certainly molecules below that. But this plays an important role in our discussion because ATP can be then generated by the hydrolysis of some of these other what are called high energy compounds, or commonly referred to as high energy compounds, like for instance phosphoenol pyruvate. It can be dephosphorylated and gives off about 61 kilojoules worth of energy. 1,3-bisphosphoglycerate gives off about 49 kilojoules of energy, and that reaction is actually shown here. 1,3-bisphosphoglycerate goes through this intermediate and undergoes ionization to 3-phosphoglycerate. That gives or yields 49 kilojoules of energy at standard conditions, right? The other one, phosphocreatine, here shown down here, this can go through a reaction, right, where it goes from phosphocreatine to creatine again, and this is going to make then or yield about 43 kilojoules worth of energy under standard conditions. Now, why is that important? Well, these three, actually, we're going to run into all three of these. They don't have a figure of that, but all three of these are means to make ATP. You can take 1,3-bisphosphoglycerate or phosphocreatine, dephosphorylate them, and as long as the beta phosphate from ADP is our nucleophile attacking this phosphate or attacking this phosphate, one of the negatively charged oxygens, a nucleophile on that ADP molecule, if that is the case, then you'll do a nucleophilic or a group transfer reaction, nucleophilic substitution, and that additional phosphate will then be added to ADP, making ATP. Okay, and there's enough energy to do that. It's energetically efficient to do that, actually. Okay, and we'll call that substrate level phosphorylation, and that will be a means of making ATP in the cell. And we'll talk about that in particular in glycolysis. We'll spend some time thinking about that. Okay. Now, another thing that's not shown here, and I think it does bear mentioning, I think it's important enough to bear mentioning, right? And that is to take this. Understand that we can take two ADP molecules and from them make ATP and AMP. And there's an enzyme called the adenylate kinase that will do this. It's found in all your cells, and it actually holds this reaction in equilibrium, so that if ADP concentrations are going up, then you can make from that ATP and AMP. If AMP concentrations are going up, you can make ADP from ATP. Okay, so and it holds this reaction in equilibrium, and Le Chatelier's principle takes over from there. Okay, right? And the delta G of this, I think, is like 0 or something like that. It's the actual free energy change is 0. It's at equilibrium. Okay. Now, the final thing in regards to this discussion is in terms of how ATP can be used in energy metabolism, and I just want to give one example of this. And what you have here is this. Ignore just that the figure that you see for right now. Let's do this. Let's do this. Glutamate, the amino acid, plus NH3. Okay, can become glutamine, right? And the delta G for this reaction is somewhere around positive 17 kilojoules per mole. Okay, so it won't happen or it doesn't, I guess I shouldn't say it won't happen, but it favors glutamate in the free form of ammonium, right? It's unfavorable, it's inorganic. Okay. However, if this reaction's coupled to ATP, and let me just draw a line right here, look at everything above the red line, what you see here is that we're doing this essentially the same reaction. We have glutamate and ammonia, and then we have ATP being hydrolyzed and and that will then make glutamine. Right? And this is a really common reaction in the cell. Now, why am I bringing this up? Well, oftentimes reactions that use ATP, anabolic reactions in particular that use ATP, are going to be drawn like this, where you just have this ATP being hydrolyzed and ADP and inorganic phosphate made or generated from that. And this gives this impression like, okay, ATP is hydrolyzed and good things happen. And it doesn't really give you an idea what happens. I mean, you could from this infer that ATP is hydrolyzed and it kind of sends these magical energy shock waves through the cells, and then the cells do things. And that's really not at all what happens. And so we want to try and avoid magical descriptions in this class. And so let's go ahead and look at what's actually happening in this reaction. The reaction actually requires this glutamate molecule to have this nucleophile, and that nucleophile then attacks the gamma phosphate of ATP, and that yields an ADP, and that gamma phosphate is now then attached to this carbon. Okay, and that's what would be considered an acyl phosphate bond. Okay. Now, what's important about that? Well, this here, that oxygen, is a really bad leaving group. Okay. However, this, as I've already mentioned, that phosphate, is a really good leaving group. And by transferring then the phosphate from ATP to the glutamate molecule, making this acyl phosphate bond, we now have introduced a really good leaving group. And so then this, and they're not showing this chemistry, but this is a nucleophile, right? That ammonia can now nucleophilically attack, okay, this electrophile, and this will be our leaving group, and what will be then generated is glutamine. And that's energetically efficient, and we have then used the energy in ATP and this introduction of this good leaving group to make glutamine from glutamate. And the delta G of this reaction, right, is less than 0. It's exergonic. Okay? Now, this is a really common, actually, step. When we get to amino acid metabolism, we'll see this quite a bit. And there are plenty of enzymes that will do this. Right? So, but this is just one example of how ATP can be used in processes in the cell. And I don't want to have this idea that ATP is hydrolyzed and then energy goes through the cell and things just magically occur. Okay? All right, so that's it in terms of ATP and the molecule. I don't think I need to say anything else. Again, if you have any questions, by all means, come and see me or consult your book or both. Okay?